So we're finally at a point where we can finish up the proof of the Cauchy criterion. So we're going to do the hard direction this time, and that is we want to show that if a sequence is Cauchy, then we know that it converges. And we've really done the hard work already. So we have already shown if A sub n is Cauchy, it has to be bounded. And we've shown, or proven the Bolzano-Weierstrass theorem, that any bounded sequence has to have a convergent subsequence. So Cauchy implies bounded, implies there's a convergent subsequence in there. And so that has to converge to some real number L. And the last piece is this claim that the original sequence converges to the same thing, capital L, as the subsequence guaranteed by Bolzano-Weierstrass. So that's what's left to prove. There's not that much to it, and it ought to look like a familiar kind of argument. So let epsilon be bigger than 0, and consider the thing that we want to show can be made small, right? We need to produce some capital N that makes the terms A sub n within epsilon of capital L. So let's use one of our favorite tricks. We're going to add and subtract a member of the subsequence and then crash through with the absolute values using the triangle inequality. And so our task is to show that this piece is less than epsilon over 2, and this piece is less than epsilon over 2, and as soon as we do that, then we're done. But the way we split this up is perfect for that, for completing the proof. We know the sequence A sub n is Cauchy, so we can make the terms here get as close as we like together. So we'll force them to be within epsilon over 2 of each other. Similarly, the subsequence, as guaranteed by Bolzano-Weierstrass, we know converges to L. So we can make the members of the subsequence get as close as we like to L, and we'll do that. So since A sub n is Cauchy, there exists some capital N1 such that as long as n and n sub k are both bigger than capital N1, that implies they're within epsilon over 2 of each other. And since the subsequence converges to capital L, there's some other n, say n2, such that if we go far enough out in that subsequence, then that difference is less than epsilon over 2. And so the last thing we do is take the larger of the two capital N's as our final capital N, and that's going to guarantee that both of these are less than epsilon over 2 at the same time. And so the original expression is less than epsilon, and we're done. So take capital N as the larger of the two from each piece, then n larger than capital N forces An minus L to be less than epsilon over 2 plus epsilon over 2, which is epsilon, and we've completed the proof. So it's a kind of a long way around to get there, but now we've got a really useful tool, especially with infinite series, for showing something converges before we know what it converges to. Right, so when we're developing tests for convergence for infinite series, for example, That's one of the things we can rely on. All right, and infinite series are up next.